The first space race was driven by geopolitical rivalry and Cold War urgency. The second space race is driven by technological acceleration, commercial ambition, planetary survival questions, and a deeper scientific curiosity about whether humanity is alone in the universe. Unlike the 20th century competition that culminated in the Apollo moon landings, the new era of space exploration is not confined to two superpowers. It is a multi-actor, globally distributed transformation involving government agencies, private aerospace companies, international coalitions, and emerging spacefaring nations. The objective is no longer symbolic victory. It is sustained presence beyond Earth. At the center of this renewed expansion are institutions that have defined space science for decades: NASA, SpaceX, and the European Space Agency. Each represents a different model of exploration. NASA embodies state-funded scientific infrastructure and long-duration research programs. SpaceX represents vertically integrated private sector innovation, focusing on cost reduction through reusability. The European Space Agency reflects multinational cooperation, pooling resources across European member states to compete at global scale. Together, these entities define the architecture of Space Race 2.0. Mars colonization has become the symbolic and strategic focal point of this new era. Unlike the moon missions of the 20th century, Mars presents challenges that are not symbolic, but existential. The planet lies at an average distance of roughly 200 million kilometers from Earth. Travel windows open approximately every 26 months due to orbital alignment. A crewed mission would require months of transit time, exposure to cosmic radiation, microgravity-induced muscle atrophy, and psychological isolation. Upon arrival, astronauts would face a thin carbon dioxide atmosphere, extreme temperature fluctuations, and a lack of liquid surface water. Yet Mars also holds scientific promise. Geological evidence suggests that billions of years ago, it possessed rivers, lakes, and possibly oceans. Robotic missions have identified ancient river deltas and mineral formations consistent with long-term water presence. If microbial life once emerged there, it may have left biosignatures in sedimentary rock layers. The search for past life on Mars is not speculative mythology. It is grounded in planetary geology and astrobiology. The physics of colonizing Mars extends beyond survival to planetary engineering. Terraforming is often discussed in popular culture, but its scientific basis requires rigorous examination. Terraforming would involve altering atmospheric composition, increasing surface pressure, and raising global temperatures to support stable liquid water. Mars' atmosphere is primarily carbon dioxide, but it is too thin to trap sufficient heat. One proposal suggests releasing greenhouse gases from subsurface reservoirs or manufacturing artificial super greenhouse gases to trigger warming. However, the total accessible carbon dioxide inventory may be insufficient to create Earth-like pressure. Additionally, Mars lacks a global magnetic field, meaning its atmosphere is continuously stripped by solar wind. Even if terraforming were achieved temporarily, sustaining it over geological timescales would be extraordinarily difficult without artificial magnetic shielding technologies. Rocket propulsion science underpins all of these ambitions. Traditional chemical rockets operate on Newton's third law. Expelling mass at high velocity generates forward thrust. Chemical propulsion remains reliable but inefficient for deep space missions due to fuel mass constraints. Advanced propulsion concepts aim to overcome these limitations. Ion engines accelerate charged particles using electric fields, achieving higher efficiency but lower thrust. Nuclear thermal propulsion, long studied but not yet deployed for crewed missions, would use a nuclear reactor to heat propellant, dramatically increasing exhaust velocity compared to chemical systems. The advantage lies in reducing travel time to Mars, thereby lowering radiation exposure and mission risk. Reusability represents one of the most significant engineering advances in modern rocketry. Historically, rockets were expendable. Each launch destroyed its primary stage. SpaceX altered the economic model by landing and reusing first-stage boosters. This reduces launch cost per kilogram and enables higher launch frequency. Lower launch cost is not merely financial optimization. It is a prerequisite for constructing large orbital infrastructure, lunar bases, and eventual Mars transit systems. Without cost reduction, sustained interplanetary logistics remain impractical. The Moon has re-emerged as a strategic objective. Unlike Mars, the Moon lies only 3 days away. It offers a testbed for deep space habitation technologies, radiation shielding experiments, and resource extraction trials. Lunar regolith contains oxygen bound within minerals, potentially usable for life support and rocket oxidizer production. Water ice deposits in permanently shadowed craters near the lunar poles represent a critical resource. Water can be split into hydrogen and oxygen for fuel, enabling refueling depots in lunar orbit. This concept, known as in situ resource utilization, reduces dependence on Earth launches. Moon mining extends beyond water. Rare earth elements and helium-3 have been proposed as potential economic incentives. Helium-3, rare on Earth, but present in lunar regolith due to solar wind implantation, is sometimes cited as a future fusion fuel candidate. However, practical fusion reactors capable of using helium-3 are not yet operational. Thus, lunar resource economics remains speculative. Nonetheless, geopolitical interest in lunar territory reflects long-term strategic planning. Beyond our solar system lies the frontier of exoplanet discovery. Thousands of planets orbiting distant stars have been detected using methods such as the transit technique, which measures minute dips in starlight as a planet crosses in front of its host star, and the radial velocity method, which detects stellar wobble caused by gravitational interaction with orbiting planets. Statistical analysis suggests that potentially habitable planets may be common in our galaxy. Habitability equations attempt to quantify the probability that conditions suitable for life arise. Factors include stellar type, planetary distance from the star's habitable zone, atmospheric composition, and planetary mass sufficient to retain atmosphere. However, detecting life requires identifying biosignatures, chemical imbalances in planetary atmospheres that may indicate biological activity. Oxygen, methane, and other gases in specific ratios can suggest metabolic processes. Future telescopes aim to analyze exoplanet atmospheres with unprecedented precision. The search for life beyond Earth intersects directly with the Fermi paradox. If intelligent civilizations are statistically likely, why have we not detected evidence of them? Possible explanations range from the rarity of life to the self-destruction of advanced civilizations to the possibility that interstellar communication is technologically impractical. The renewed space race also intersects with contemporary debates about unidentified aerial phenomena in the United States. Official investigations have acknowledged unexplained aerial observations without confirming extraterrestrial origin. While no scientific evidence currently supports alien visitation, the cultural fascination reflects humanity's broader curiosity about extraterrestrial intelligence. Scientific inquiry demands empirical validation. The absence of confirmed extraterrestrial contact reinforces the importance of systematic exoplanet exploration rather than speculation. Mars colonization narratives often emphasize planetary backup for humanity. Earth faces climate change, biodiversity loss, and geopolitical instability. Establishing a self-sustaining settlement on another planet could, in theory, safeguard human civilization against extinction-level events. However, creating a closed-loop ecological system on Mars capable of long-term independence is vastly more complex than sustaining life on Earth. The technological requirements include radiation shielding habitats, artificial gravity solutions, controlled agriculture systems, and autonomous manufacturing capabilities. Psychological factors also play a critical role. Long-duration missions in confined environments impose cognitive stress. Research from Antarctic stations and orbital missions provides partial analogs, but interplanetary isolation magnifies challenges. Communication delays between Earth and Mars can reach 20 minutes each way, preventing real-time assistance. Autonomy becomes essential. Astronauts must function as engineers, scientists, medics, and problem solvers without immediate Earth support. Economically, the commercialization of space introduces new dynamics. Satellite constellations for global internet coverage generate revenue streams that subsidize research and development. Private investment reduces reliance on taxpayer funding alone. However, commercialization raises regulatory questions about orbital congestion, space debris, and resource ownership rights beyond Earth. International cooperation remains vital. The European Space Agency collaborates on scientific missions and technology development, often partnering with NASA. Shared missions distribute cost and expertise. However, competition persists alongside collaboration. The dual nature of cooperation and rivalry mirrors the original space race, but within a more interconnected global framework. Terraforming physics remains speculative but grounded in thermodynamics and atmospheric science. Increasing planetary albedo, Introducing greenhouse gases and modifying orbital mirrors to concentrate sunlight are theoretical approaches. Yet the energy requirements are colossal. Altering a planet's climate intentionally demands planetary-scale engineering far beyond current capacity. Terraforming may remain a centuries-long vision rather than a near-term objective. Rocket propulsion advancements may determine feasibility timelines. Nuclear propulsion could shorten Mars transit to weeks instead of months. Research continues cautiously due to safety and political considerations. Advanced concepts such as plasma drives or fusion-based propulsion remain experimental. Each incremental improvement reduces mission risk and expands reachable horizons. Exoplanet habitability research also reshapes philosophical perspectives. Discovering microbial life elsewhere would redefine humanity's uniqueness. Discovering intelligent life would transform civilization. Yet even without direct contact, the statistical probability of habitable worlds shifts existential narratives. Humanity may be one of many life-bearing species in a vast cosmic ecosystem. The Fermi paradox remains unresolved. One interpretation suggests that technological civilizations are short-lived. If so, sustainability becomes not only an environmental issue, but a cosmic filter determining survival duration. The ability to manage planetary ecosystems responsibly may correlate with longevity of intelligent life. Space Race 2.0 is therefore not merely technological competition. It is a convergence of engineering, astrobiology, geopolitics, economics, and existential philosophy. NASA advances scientific research and deep space mission planning. SpaceX accelerates launch cadence and cost reduction. The European Space Agency strengthens multinational collaboration. Together they represent a shift from exploration as spectacle to exploration as infrastructure. Mars colonization challenges biology, engineering, and governance simultaneously. Moon mining tests resource independence beyond Earth. Exoplanet discovery expands cosmic context. UFO debates reflect cultural fascination, but require disciplined scientific evaluation. Terraforming physics illustrates the scale of planetary engineering required for transformation. Rocket propulsion science dictates practical timelines. Habitability equations guide our search for life. The Fermi paradox frames the silence of the cosmos. The second space race unfolds not as a sprint but as a sustained campaign. It is driven by scientific curiosity and strategic necessity. Its success will depend on propulsion breakthroughs, sustainable habitat engineering, international governance, and economic viability. Space content remains evergreen because it addresses fundamental human questions. Where did we come from? Are we alone? Where are we going? The expansion into space is not escapism. It is an extension of scientific inquiry and survival strategy. As launch frequency increases and lunar missions resume, the foundation of a multiplanetary civilization begins to form. Whether humanity ultimately establishes permanent settlements on Mars or merely deepens robotic exploration, the trajectory has shifted irreversibly outward. Space Race 2.0 has begun, and its outcome will define the long-term arc of human civilization.